Hi everyone, Phil from statisticsmentor.com. In this video, we're going to be proving two results. If set A is a subset of B, in other words, if A is contained in B, or is equal to the set B, then probability of A is less than or equal to probability of B. But the converse is not true. In other words, the fact that if probability of A is less than or equal to probability of B, it does not mean that A will be contained in the set B. And it's the second point that motivates me to make this video, because in the homework this week I have my second year students using the result that if probability of A is less than or equal to probability of B, implies that A is contained in the set B, which is not true. And I'm going to do two proofs. I'm going to prove this one, and we're going to prove this one. Now guess why they've got the wrong result for this is because when we first teach them, this result, we don't mention that the converse is not true. So I'm telling you the converse is not true. Right, the first proof, we want to show that if A is contained in the set B, then probability of A is less than or equal to probability of B. Let's try to picture that. Well, here you go. I've got the sample space S, which is represented by this box here, this set A, and let's say this yellow blob is set B. Then clearly B is contained in A. Well, what's the idea of this proof? Well, with these kind of proofs, we apply the axiom of probability, which are the basic kind of basic results of probability. Since we want to show this, we want to get some kind of expression. Probability of A is equal to probability of B plus some positive number, which then implies that this must be true. Okay. How do we get such an expression? Well, using the axioms of probability, the things with these kinds of sets is that we want to rewrite the set A in terms of the union of mutually exclusive sets, otherwise known as disjoint sets. And we can do it like this. A, if we look at A, this whole set of A is equal to B, and the rest of A, not including B. In other words, it's equal to this blob, or everything except for that blob. Yes, it's like a jigsaw. If you put those two together, this into that hole, then you're going to get A. And you can see that this does not overlap with any other thing, which means that it is mutually exclusive. So it's OR, and we'll put in brackets here A and not B, because that's what this is. If we shade it, it's A and not B, gives us this bit here, except for the blob there. Now we can see that this set and this set are mutually exclusive. In other words, they do not overlap, and so we can apply the axioms of probability to say that probability of the union of these two things is the sum of the sets. In other words, let's just write it here. Probability, we're using the result, I'm using different A and B's here. Probability of A and B, if A and B are mutually exclusive, that is equal to probability of A plus probability of B. That's the result. So we'll apply this here. Since B mutually and A and not B are mutually exclusive, so it must be that the probability of A is equal, I'm not using a result right here yet, let's see. since the mutually exclusive must be this now, is equal to the sum of the probabilities. Like so. And now we've got this expression we said we were heading for before. We wanted something of probability of A equals probability of B plus some positive number, which we have, because since this term here, all probability bigger or equal to 0, and of course less than or equal to 1, it must follow that probability of A is bigger than or equal to probability of B, where equality holds if this probability is 0. Done. So to recap, we've used the axioms of probability, and the idea here is that we want to split up the set A into this union of mutually exclusive sets, in which we can then apply the axioms of probability, that the probability of union of mutually exclusive events is the sum of the individual probability of those events. Done. Right, secondly, probability of A is less than or equal to probability of B does not mean that A is a subset of B. Now, while on this theme, subset here, you see in some other textbooks some authors use, instead of this notation, they use this to mean the same thing, which for some people can be quite confusing, because this looks like it's contained in A but not necessarily equal to A. The sets may not be equal. Okay, so we can prove this by counterexample. In other words, give an example where it does not hold, and that's sufficient to say that this doesn't hold. Well, let's consider the outcome of a die. So if we toss it once, the sample space is 1 to 5. 1 to 6. And then let's just say, let's set up two arbitrary sets where one is smaller than the other one. We want to set it up so that, let's see, so that probability of A happening will be less than or equal to probability of B happening. So let's say A is just outcome 1 and B is all the other outcomes 2, 3, 4, 5, 6. Now this is not the only example I could give, but I'm just giving you an example. A is outcome 1, B is all the other outcomes. Then clearly we can see that what's the chance of A happening, i.e. what's the chance of getting 1 when you toss a die? It's 1 over 6. 1 out of 6. And what's the probability of B? Well, how many members you got? 1, 2, 3, 4, 5. 5 out of 6. So clearly probability of A is less than probability of B. But is A contained in B? No, because you see here this is B and A is not in B. In other words, we've just shown that even though probability of A is less than probability of B, it doesn't mean that A is contained in the set B. And that's it. So proof by counter example.